Welcome to The Explainer. Today, we're basically scientific detectives on a mission to solve a chemical case. The mystery? Just how much stuff is really in a solution. And our secret weapon is a brilliant little principle called Beer's Law. Let's dive in.
Okay, so imagine this. You've got this beaker of blue liquid. It's copper 2 sulfate. We know what it is, but we have no idea how concentrated it is. How can we figure out the exact amount that's dissolved in there without just, guessing?
Well, it turns out there's a really elegant way to do it. And it's all thanks to one fundamental scientific principle. So, it's time to introduce our mystery-solving tool, Beer's Law.
So what is Beer's Law, really? At its heart, it's actually super simple. The more stuff you have dissolved in a liquid, the more light it's going to block or absorb. That's it. This direct relationship is the whole key.
Think about it like this. Remember making juice from concentrate? If you only use a little bit of concentrate, the juice is a pale color, kind of watery. It's less concentrated. But if you dump a lot of concentrate in it, it gets way darker and the flavor is intense, right? It's more concentrated. Beer's Law is just a way of putting numbers to that exact idea. The lighter, weaker solution absorbs less light, so it has a lower absorbance. The darker, stronger solution absorbs more light, giving it a higher absorbance. Simple as that.
And here is where the magic happens. When you plot the absorbance against the concentration, you get this beautiful, perfect straight line. And this isn't a coincidence. It's a direct, linear relationship. And that predictability, that's what our entire experiment is built on.
Okay, so we've got the principle down, but how do we actually apply it to figure out the concentration of our mystery blue liquid? I mean, we can't just stick it in a machine by itself. First, we have to build a kind of reliable reference guide.
Exactly. To figure out where our unknown is, we first need to draw a map. And in chemistry, we call that map a standard curve. We're going to create it by making a whole series of solutions where we know the exact concentration of each one. And here's the recipe for our map. We're going to take very precise amounts of our main copper sulfate solution, that's the stock, and mix it with pure distilled water. By changing up those ratios, we create 5 different solutions, each with a very specific known concentration, from a light 0.080 molar all the way up to our original 0.40. These are going to be the known landmarks on our map.
So the actual lab work is pretty straightforward. First, we mix up our 5 standard solutions. Next, and this is super important, we have to calibrate our measuring device. We do that using what's called a blank, which is just a sample of pure water. It basically tells the machine, hey, this is what 0 looks like. Then, we just go down the line, one by one, and measure the absorbance of our 5 known solutions. Now, this stuff might seem a little picky, but in science, precision is absolutely everything. A tiny fingerprint, a little air bubble, or even just putting the sample container in sideways can completely throw off your data. So wiping the container, handling it just by the edges, and making sure the light has a clear path, these little details are what make our map accurate.
All right, we've done the prep work, we've made our standards, we've taken our measurements, our map is officially ready. Now comes the exciting part. Let's actually use it to find our unknown. So, we take the 5 absorbance numbers we just measured, and we plot each one against its known concentration. Then we connect the dots. And there it is, our beautiful straight-line standard curve. This is our perfectly drawn map, ready to go.
Okay, map's made. Time for the final piece of the puzzle. We take our beaker of that mystery blue liquid, we put a sample into the machine, and we hit measure.
And we get a number. The machine tells us the absorbance of our mystery solution is 0.662. We are now one single step away from solving this thing.
This is it. This is the aha moment. Look at the graph. We find our number, 0.662 on that vertical axis, the absorbance axis. Then we just trace a line straight across until we hit our standard curve. The second we hit that line, we drop straight down to the bottom axis. And bam! There's our answer. That's the concentration. Just like that, we've solved the mystery.
So, we solved it. Case closed, right? Well, not so fast. Let's do a quick reality check because it really highlights why all those careful little steps we took were so incredibly important.
Let's just play out a scenario for a second. What if there was a mistake made way back at the beginning? What if the main stock solution we used was actually a little too watery because someone made a mistake? What do you think would happen then?
Well, that one single mistake would create a domino effect.
every single one of our 5 known solutions would actually be weaker, less concentrated than we thought they were. All of the landmarks on our map would be in the wrong spot.
And if your landmarks are wrong, your map is basically useless. The line you draw on the graph would be totally off, and it would lead you to a completely wrong answer for your unknown. It just goes to show you, this entire powerful technique depends on being careful and precise right from the very first step.
You know, today we use light to find out how much blue stuff was in some water. But think bigger for a second. This same basic technique is used everywhere. To find tiny amounts of pollutants in a river, to analyze blood samples in a hospital, to make sure your favorite drink tastes the same in every can. The world is full of unknowns. What are you going to discover next?